Okay, so I hope it's all set up and visible to everyone. So as the last speaker, I guess it's customary to sort of start with a few thank yous, particularly the organizers, so Alex, Tony, Tim, and particularly Nathan. Thank you for organizing this day today to commemorate Richard. So thank you very much. And I think I also want to thank Rachel and Sam for being here all day long, for allowing us to share our life with Richard. I know, and we talked about this, Richard, sort of, you're probably not very familiar with his life here, and you know him in a very different way than we know him. And it's sort of very nice to, I think there are some overlaps in how we know Richard, but it's very nice of you to have been here. Also, I had to think a little bit of what to talk about, and I had one paper with Richard from 2003, together with Vladimir Rittenberg, with whom I collaborated quite a bit at that time. And I'm going to talk about that work because it's about a sort of a nice idea stripped down to its bare bones simplicity, and where we could do something nice. Before I do, I have two photos that Rob Mayday was kind enough to share about a joint sort of, well, brief holiday we had doing a rowing along the Great Ocean Road with the Maydays and us. And this is a photo near the Airy Inlet's lighthouse. And it shows the playfulness of Richard. We're trying to measure the circumference of the lighthouse, and we're using all family members there. And so very good memories. And this is, I don't exactly know, 2015 or so thereabouts. Yeah, so very good memories, Richard. In recent times, I've worked more administratively with Richard in the past few years. So we had a lot of fun in doing the lecture allocation together. So, yeah, but his approach was very important in sort of disarming potential conflicts of interest people may have had. Lecture allocation is always kind of a delicate thing to handle, but his involvement made it, I think, work well in the school. So, and it was a real pleasure to work with him. And I know that Alex, as a previous head of school, also had that. It was a wonderful colleague to work with and very reliable person, so we'll miss him. Okay, a little bit then about my collaboration with him, and hopefully we can still end on time. So the idea is quite simple. What we want to do is describe a stationary state of a Markov chain. So my interest is in non-equilibrium statistical mechanics, and most of the talks today have been about equilibrium statistical mechanics. At the time, and I'm still am interested in stochastic processes, and one of the things you can look at, one of the simplest things you could look at, is the steady state to which you converge as time goes to infinity. And you want to describe that mathematically, so you want to understand what that looks like. And on fairly general grounds, if you have some Markov chain with some variables which are rates, and I'll get a bit more specific soon. The steady state is a vector in which the elements are all positive polynomials in your variables, in the rates of which the events happen. And being a sort of polynomial with positive coefficients, you might wonder, well, is it a partition function or a generating function of something? There's no reason that it should be. But if it is, then it could be a generating function of some sort of combinatorial model or an equilibrium Statmet model. And if so, does the phase diagram or the phase behavior of that fictitious model tell you anything about the stochastic process? And it's a big open problem in physics to have a macroscopic thermodynamic theory of non-equilibrium systems. And so this was a sort of a question that might be an approach towards forming such a theory.
And what we did with Richard and Vladimir is to strip this idea down to the very simplest of examples to show you that that's sometimes possible, and that an equilibrium Statmet model can describe a stationary non-equilibrium process. So I have to work through a little bit of notation. Hopefully it's not too bad. At the top, so I'm going to label configurations of some stochastic process as A, and Pt of A is the probability to find such a configuration A at time t under the rules of the process. And the rules are given by this Markov chain equation. It says that the rate of change of the probability, so the time derivative, is given by this right-hand side, which is if you happen to be in some configuration B, and there is a transition R from B to A, then that adds to the rate of change of the probability to be in A. And likewise, if you were in A, but there is a rate to get out of A, then that contributes negatively to the probability to remain to the rate of change to be in A. So this is a linear equation for P, and so you can write it in matrix form. So there's physics cat notation that there's different ways of writing it, but you can just say the rate of change of a vector P of t for which the elements are time dependent is just given by a matrix M times that vector, where M encodes all these rates and events that can happen. It's called the transition matrix. And the off-diagonal elements are the rates. These are all positive, because they're like probabilities, if you like. Yeah, so that's a Markov chain equation. And then you're interested in the infinite time limit. When t goes to infinity, you call that the stationary state. And that stationary state satisfies the property that its rate of change is 0. Hence, that if the matrix M acts on this vector, it should get 0. So it's an eigenvector. Its eigenvalue is 0. And this is formally solved by the cofactors of the matrix. So let's X be a cofactor of M. So you remove the bth column and the bth row, and then you take the determinant. Then that forms the element of the, well, that's equal to P of B, up to an overall normalization. The proof is simple because M, the determinant of M is 0, it being a transition matrix, and all its columns add up to 0, so the determinant has to be 0. And then you just use a cofactor expansion of M, of the determinant of M, and you'll see that you exactly get the Markov chain, the right-hand side of the Markov chain equation, and that needs to be 0. So the x's are solving the stationary state equation. So this is a formal thing because this matrix M is huge, it's very large, and you can't just simply compute these cofactors, but it tells you a few properties. In particular, so up to an overall normalization Zn, where n is the size of my system, the stationary probabilities are given by cofactors divided by Z of n. And Z of n is just the sum of all the cofactors. It's some number depending on the model. Okay. So the properties are, and this is part of what's called the matrix tree theorem, that this normalization Zn is a homogeneous polynomial in the rates R with positive coefficients. Some of these rates can be 0, or many of them can be 0, but in general it's a homogeneous polynomial in the rates R with positive coefficients. And so you can wonder, is it a generating function of something? And so you might think, do these rates represent some, do they have an interpretation of Boltzmann weights? And do they count certain statistics? So you want to think of the normalization of a steady state as a generalized partition function. And we can think of the quote free energy in what we would normally do in equilibrium Statmet, take minus the log. And then we would think of taking the derivative with respect to these Boltzmann weights, or generalized Boltzmann weight Z, as some numbers of observables of things, and particle numbers. And we may also think that if we let n go to infinity, that could be like a volume thing of my fictitious Statmet model. And if that limit sort of exists as n goes to infinity, then I might convert these fictitious particle numbers as densities. And then start thinking about building a phase diagram of this fictitious type of Statmet model and ask whether that would tell me anything about the non-equilibrium model. So the comment below is a disclaimer that I won't go into right now. And so with Richard, we worked on this, and this is a huge, quite a complex type of question. And we went to a very simplified model to test this idea. And the model that I've spent quite a bit of time on, and Richard as well, is this asymmetric exclusion process. And I'm going to use a simple version of it where you have particles moving to the right, so they can only move to the right, not to the left, over time. And there are reservoirs at the ends. At the left, particles can enter with some rate alpha, and they can leave at a rate beta. And it has many different types of applications. In biology, road traffic work with Tim a lot on that. But it has really nice, this version of it has really nice, beautiful, pretty mathematics, including Richard's beloved dictats. So if you're interested in the stationary state of this model, there's a theorem, there's a way of constructing it using some mathematical tricks, where if you encode the sequence of particles with these variables tau 1 up to tau n, so tau is 0 if there's no particle and 1 if there is a particle, then you can compute the steady state by inserting matrices D and E. So for every one, for every particle you insert a D, and for every whole, so when tau is 0, this is 1, you insert an E. So you have a product, a string of products of matrices, and then you sandwich it between two vectors, W and V. And if you choose these correctly, you take the product of matrices, you sandwich between two vectors, you get an expression out of it, which is exactly well, that's the claim. It's the probability to find that particular configuration in the steady state. And these matrices, they have to satisfy certain relationships, which we call algebra, and the relationships are here. So there's DE is D plus E, and then there's relationships when the D acts on the right vector V, or when the row vector W acts on E. There's a relationship. So you have to solve these relationships and write an explicit form for the matrices, or you just use the rules, and then that allows you to compute these probabilities. And if you're interested in the normalization, so summing over all possible configurations, then the expression becomes particularly simple. What you have to do is add D plus E raised to the power n, and then send it between the two vectors, and that will give you the normalization. So given a particular model, and here's a simple one, solve the corresponding algebra, and in this case that can be done, and a lot of people have looked at it, including Richard, and then compute this quantity here. And what we're asking now is there an alternative interpretation of this quantity here as a two-dimensional, I'll take it back, an alternative interpretation as a statistical mechanical model, equilibrium. So we want to think of these matrices D plus D and E, which are just some auxiliary matrices in this setup to compute a steady state. Do they have an interpretation of, say, a transfer matrix, like a statistical mechanical transfer matrix? And do they build up a Statmet model? And then can I think of Zn now as a partition function or a generating function? And that is what we did with Richard. And yes, you can. And that is the one transit walk model. So it's dig paths again. You start at the origin to the left, then you have a dig path above the x-axis for a while, and at some point you are allowed to go down and cross the x-axis, and then there's another dig path below the x-axis, and you have to bring close. But you can only go down once. You can go down, you can cross the axis anywhere. It doesn't have to be in the middle. You can cross anywhere, but as soon as you cross, you can't go back up. So you can cross once. Moreover, we associate some surface energies as occurred in the earlier talks today, people from Canada and France. So every time you hit the axis and go back up, there's an energy associated to that. So we give it a Boltzmann weight 1 over alpha if you hit it from above, and a Boltzmann weight 1 over beta. Here, 1 over beta if you hit it from below. So it's a simple walk model of the type we've seen many times today. It's one of the very simplest cases of the type of models that have been talked about today and studied. One big path, it can go down below the x-axis once, and it has some surface absorption weights. And my claim is that the statistical mechanical partition function or the generating function of these walks with these absorption weights is exactly the same as the normalization of my stochastic process. So here we have a very simple example of a stochastic process for which the normalization of the stationary state does indeed have an interpretation of a fairly natural statistical mechanical model. And then you can ask all sorts of questions about this model in using the methodology in thermodynamics, all the techniques that we know very well, and that will then inform the behavior of the stochastic process for which such a global theory doesn't exist. Right? So it's just a very bare bones example, and of the type that Richard really liked because it's so simple. So that model is really easy to solve if you work in the field for a long time. So Richard sort of almost immediately write down the generating function. It has a common factor alpha times beta out in front. And then you have to sum over, and then there are some combinatorial numbers here, which are Ballot numbers. They have some expression which I've listed here. There's a lot to say, but I won't. And then here are the entrance of the alpha and beta, which were the entrance and exit rates of my stochastic process. They enter here as Boltzmann weights, essentially. And there are different ways of writing the formula. You can write this formula here on the second line as the generating function of a dig path of length p with absorptions alpha, and then at side p you dive below the x-axis, and then what remains is the generating function of dig paths with contact rate beta that touch from below of length n minus p. And because the place where you go below the x-axis is arbitrary, you just sum over p, sum of all possible positions that you can dive below. So that is the generating function. Okay. Then you can do the asymptotics. These expressions are very well known to many people here in the audience. There's just a dig path generating function with a fugacity at the absorption. Depending on whether this fugacity is larger or less than a half, the asymptotics are different, because
the walks may be attached to the surface if your energy is attractive, or it may be free if your energy is repulsive. And Z equals a half is sort of the sweet spot where you have that phase transition. So another speaker talked about that earlier, maybe Gary did. But now I think of this as a grand canonical partition function, and we can compute the contact averages as derivatives of this grand canonical partition function, treated as a equilibrium model, and analyze the phase diagram, which I should have on the next slide. I do want to point out now that we can relate the non-equilibrium quantities of the exclusion process, such as the current. There's a flow of particles that has a current, the density rho of the particles in the stochastic process. We can relate them to the density of contact points in the walk model. So there's this relationship between the non-equilibrium quantities rho and j and the equilibrium quantities a and b, and alpha and beta. So there's a really nice correspondence. And so, of course, the question is, to what generality does this hold for more realistic systems? But this is sort of a nice model to illustrate the ideas and concepts. So the phase diagram of the Statmet model is this. If alpha and beta are large enough, then the walks on both above and below the x-axis are dissolved. They are free to wander about. The energy to attract them to the surface is not very strong. If, however, alpha is smaller, then one of the walks is absorbed, and if beta is smaller, the other one is absorbed, and then there is a sort of a line in between. Both are sort of dissolved, but the point where you cut through is uniformly randomly distributed across. And this is also the task set phase diagram. For those who work in the area know this diagram very well. It's exactly the phase diagram of the exclusion process and many other stochastic processes. And the funny thing is that the original stochastic process is a many particle system of interacting particles, and this phase diagram is really like a one particle phase diagram, if you think about it. And the one fictitious particle is really the sort of the coordinates of the particles where you intersect the x-axis with your walk, and that really determines this phase diagram. If your model is more complicated, you can go to ASA, where you introduce backhopping or other additions. This diagram is fairly robust against such extensions. So it's already here in this sort of very simple setup. You're capturing quite a bit of the essential features of this type of stochastic process. All right. I think I will leave it there because we're right on time. Thank you.
Thanks very much, Jan. I think we've got time for one or two quick questions. Do we have any online questions? Any in-room questions?
I have a question.
Yeah.
Okay.
Mario.
May I? Okay. Thanks, Jan, for your very wonderful talk. I have a question regarding the very broad picture. You have only with the exclusion, totally antisymmetric exclusion process, chosen a very well, more or less simple model, but the general starting point was exactly with the potential. do you mean regarding the convex potential also interactions, or otherwise when the interactions are not completely involved, there, I would say you need also a certain growth condition for the convexity. Otherwise, I don't think that stationarity is immediately guaranteed. Well, I know it already from randomatic theory with the eigenvalues. When it's not growing fast enough, it can spread out.
So I'm not exactly 100% sure what you're asking, Mario, but the very simple idea is that we look at the stationary state of the stochastic process. This is automatically a positive polynomial. As I agree that the growth rate of that polynomial doesn't have to correspond to any 1D or 2D Statmet problem. It's just a positive polynomial, and so it would have convexity properties, and we could think about it. So
okay. This means you need.
I wouldn't expect the overall scope to be fully generally holding, but there could be classes of models for which you could use this analogy.
Okay, but you say polynomial growth. Okay, this I missed this point. Okay, thanks.
Any other questions? Thanks very much, Jan. Remains to me to thank all the speakers, especially those who from overseas who stayed up to all hours. In fact, the number of international speakers that we've had compared to the number of local speakers, which are approximately equal, I think attests to the high regard Richard enjoyed, not just locally, but internationally. I also like to especially thank Rachel and Sam for enduring what must have been a bizarre experience, listening to us all. And I hope you've been taking notes, as there'll be a short examination at the conclusion of this meeting. Well, we've really had quite a tour of mathematical physics, algebraic combinatorics, lattice path problems, number theory, which I think reflects the broad range of Richard's mathematical research. I hope we've done justice to his scientific legacy. And I know it sounds ridiculous, but I'm sure Richard would greatly have enjoyed being here today and listening to the program. As is clear, I think, from the comments that various speakers have made, Richard was greatly respected and appreciated for his scientific integrity, his ability, and his enthusiasm. It's said that the ancient Egyptians, after you died, you are asked 2 questions to which you must answer yes to enter the afterlife. And those questions were, did you experience joy, and did you bring joy? I think it's clear that Richard is now enjoying the afterlife. So thank you very much.